Hello students, welcome to my YouTube channel. In this video lecture, we are going to answer questions from sample paper number 7, BALI navigation book. Let's begin. Question number question number 11. VMCA is a minimum speed uh, is defined as the minimum speed while in the air that directional control can be maintained with one engine failed or one engine inoperative. So with use of full rudder deflection, maximum 5-degree bank, both 1 and 2 are correct. So VMCA is a minimum controllable speed in the air. Okay, this is the speed. This is the minimum speed that you should fly at if one of the engines fail. And with this speed, you can use maximum rudder deflection, left rudder, right rudder, and you can do a maximum bank of 5 degrees. So both options are right. So correct answer is Charlie. Both 1 and 2 are correct. Question 12. Maximum allowable takeoff mass is given. Landing mass, zero fuel mass, DOM, traffic load, trip fuel, takeoff fuel are given. Find maximum possible additional load. Okay. So takeoff mass, make the three columns like I always do. Landing mass column, zero fuel mass column. In the takeoff mass column, you are going to write a value which is the lesser of maximum structural takeoff mass and performance limited takeoff mass. In the landing mass column, you are going to write a value which is the less of maximum structural landing mass, performance limited landing mass, and to that you are going to add trip fuel. In the zero fuel mass column, you are going to write a value which is zero fuel mass plus fuel on board. So over here, maximum takeoff mass is given, performance takeoff mass isn't given. So which is 64,400. 64,400. Landing mass 56,200. So 56.2. Trip fuel is 4,900, which is 4.9. Zero fuel mass 53,053. Fuel on board, minimum fuel on board 7,400. So 7.4. So 56.2 plus 4.9 is 61.1. 53 plus 7.4, 60.4. Now choose the least takeoff value. So the least number is 60.4. This becomes our regulated takeoff mass, 60.4. Step 2, regulated takeoff mass equals to payload plus DOM plus fuel on board. So 60.4 equals to, what is DOM? 35.5, fuel on board 7.4 plus payload. So payload will be equal to 60.4 minus 35.5 plus 7.4, 42.9. So that is equal to 17.5 or 17,500 kg. Okay. So find maximum possible additional load. So currently you are carrying a traffic load of, current load is equal to 14,500. What is the capacity? Capacity is 17,500. So that means there is space for additional load of, for an additional load of 17,500 minus 14,500, which is equal to 3,000 kg. Next, dry operating mass is given, payload is given, reserve fuel, alternate fuel, contingency are given, estimated landing mass at alternate aerodrome. Okay, at alternate aerodrome will be what? So let's say this is your departure airport. This is your destination airport, and this is your alternate airport. Now your aircraft will take off from this departure airport, fly towards destination airport, but due to some contingency, the pilot decides to divert his aircraft from this destination airport and go towards alternate airport. Go to alternate airport. Okay. So at the time of at destination, the weight of this aircraft will be dry operating mass plus reserve fuel plus contingency fuel plus alternate fuel. Trip fuel will be consumed from going from point A to point B. So subtract trip fuel. Now when you go from here to the alternate airport, the weight of the aircraft will be DOM plus reserve fuel plus contingency fuel. You will use this remaining alternate fuel from going from this airport to the alternate airport. Okay, so dry operating mass 33,510, reserve 983, alternate no, contingency 102, and you are going to add this payload also 7,600 plus payload passenger load 7,600. So 33,510 plus 983 plus 102 plus 7,600 is 42,195. So the weight of this aircraft at the time of landing at alternate aerodrome will be 42,195. Subtract alternate fuel because you are going at alternate. Next, a pitot tube covered by ice which blocks the ram air inlet will affect following instrument: VSI, altimeter, ASI. Now, all these three pressure instruments, namely your ASI, your VSI, and your altimeter, are pressure instruments. All these three instruments work on static pressure. They work on static pressure. So there will be a static pipeline joining all these three pressure instruments. Okay, there will be a static pressure pipeline. Now ASI is the only instrument, pressure instrument, airspeed indicator is the only pressure instrument which also works on pitot tube, which also works on pitot tube, that is pitot pressure. So if there is any blockage in this pitot tube from ice, dirt or whatever, it will directly affect your airspeed indicator. But it won't affect VSI or altimeter because they do not work on pitot pressure. They only work on static pressure. So correct answer is a pitot tube will affect airspeed indicator instrument. In the ATIS flight plan, item 15, when entering a route for which standard instrument departure, standard terminal arrival procedure exists, both SID and STAR should be entered. Only STAR should be entered. Both SID and STAR are not required to be entered. So, this is your flight plan. And over here, there is item number 15, cruising speed, level you're going to cruise at, and route. Now, in this route section, you're going to include your standard instrument departure route and your standard terminal arrival route. So, both routes must be included. Okay, if your airport has this SID and STAR procedures. NDB signal crossing from land surface to sea surface bends away from the normal and its speed increases. So let's say this is your land surface coastal area and here is your NDB station. Okay, here is your NDB station. So this station will transmit radio signal, and when this radio signal crosses the coastline, it will bend away from the normal. It will bend away from the normal. Okay, and what will happen to the speed of this signal? The speed will increase because sea surface, a water body, offers less resistance or less friction than a land surface. So NDB signal speed increases and the signal bends away from the normal. The still air distance in the climb is 189 nautical miles. Time is 30 minutes. What ground distance would be covered? What ground distance would be covered in a 30 knot headwind? So, distance. It's a still air distance, that means we are flying in calm atmosphere. Distance equals to 189 nautical miles. Time 30 minutes. Ground speed will be equal to your true air speed because you are flying in calm atmosphere. Okay. So distance divided by time. So 189 nautical mile divided by 30 minutes into 60. Convert that into hours. So 189 into 60 divided by 30 is 378 knots. Now, there is, you're getting a headwind. Now, in a headwind of 30 knots, your ground speed will be true airspeed minus headwind component. So, true airspeed is 378. Headwind is 30. So, 378 minus 30 is 348. Time is going to remain same, zero point 0.5 hours, 30 minutes. So distance now will be speed into time. So 348 into 0 0.5, that is 174 nautical miles. What is the operational limit for runway slope? So your runway slope cannot exceed plus minus 2% upslope or downslope. Next. Transverse Mercator charts are highly suitable for north-south extensions, east-west, north-south and east-west. So correct answer is Bravo, east-west extensions. Transverse Mercator chart, the point of tangency is along a particular meridian. So all meridians are easterly or westerly, right? East-west meridians. So option Bravo, east-west extensions. Which ICAO document is referred for flight plan? So remember document number 4444. Simple. So this concludes the lecture. I hope you have understood all the 10 questions that I have answered in this video lecture. If you have any questions, let me know in the comment box. In my next video lecture, I will solve the next 10 questions. So don't miss that lecture. I'll see you there.